Hello and welcome to week 7, lecture 1 of CO 442642 graph theory. Today we'll be discussing brambles and grids. So what is a bramble? Well, let me first ask a more general question. When does a graph have large tree width? So last class we discussed tree decompositions and tree width where you attempt to minimize the width of a tree decomposition. So a natural question is, when does a graph have large tree width? Well, to do that, I need a definition. So first, touch. Let G be a graph, and given two subsets A, B of the vertices of G, we say they touch if either they intersect or there's an edge with one end in A and the other end in B. Given that, I can tell you what a bramble is. So here's the definition. A bramble B in a graph G is a collection of connected subsets of V of G that are pairwise touching. So it's important that they are connected, and then each pair of them either has a vertex in common or again an edge between them. So pairwise touching. Now we say a cover of B, cover of this bramble, is a subset X of the vertices of G such that X intersect B is non-empty for all B in script B. So that's a cover, so if you kind of make sure you cover all of the sets in the bramble, and then we can define the order of the bramble as the minimum size of a cover of B. So that's a bramble, that's cover, and that's the order. So this should seem a little bit like tree decompositions in width, but in some weird dual form. And indeed, that's actually what Seymour and Thomas proved in '93. That a graph has tree width strictly less than k if and only if G contains no bramble of order greater than k. So having a large bramble would preclude you from having tree width and low tree width and vice versa. And the numbers are a little weird here again because tree width subtracts ones. So basically if it wasn't for that, subtracting of 1 would be, okay, you don't have k, then you'd have to have a bramble k plus 1. Here it's, tree width is either k minus 1 or you get bramble of order k plus 1, just because of how that numbers work there. So this is a very nice theorem. It's called the tree width duality theorem. It really characterizes very nicely exactly when you don't have low tree width, so you have large tree width. So it gives a very nice character, tree width, tree decompositions are very nice, and somehow they're fundamentally related to this idea of having kind of lots of pairwise touching connected sets that that can't be covered with few vertices. Okay, well, how are we going to do this? Well, the forward direction is relatively easy, so we'll do that on the next slide, that if you have small tree width, then you can't contain a bramble. The other direction, though, is much harder, so we're actually going to spend an entire lecture just on proving that, the backward direction, that if you don't have large brambles, then you indeed get small tree widths, where we have to produce a good tree decomposition. So that's next time, but for now let's do the forward direction. All right, so how do we prove this forward direction? So again, forward direction is small tree width implies no bramble. Well, think of, if we have small tree width, that means we have a tree decomposition TV of G of width strictly less than K. So let's fix one, and then consider any bramble B. And the claim is that there exists a bag of this tree decomposition that is a cover of the bramble B. So maybe if you want to think about and stop for yourself and pause and prove this, you could, but I'll go through the proof. So how do we do that? Well, suppose not. We can go by contradiction if you want, and then I'm going to use this orientation of tree technique. So if you haven't seen this before, it's kind of a general proof technique where maybe you have a tree and you orient edges, and then there always has to be a sink in such an orientation of a tree, and we're going to use that to figure out which bag should be the one that is a cover. So how do we do this? Well, how do we orient these edges? Well, consider an edge, T1, T2 of T. Then they have bags, VT1, VT2, intersect them. So look at the intersection of the two bags. Certainly, since it's a subset of both bags, it does not cover the bramble. So that means there exist sets in the bramble that are disjoint from this intersection. And if you think about it, since all these such sets mutually touch, there's a unique component of t minus e that contains such sets. So there's a unique direction where the bramble lives. We orient the edges kind of then towards the direction where the bramble lives. So we do that, and so we orient E toward that component, and then since T is a tree, there exists a sync T of the orientation, right? If every vertex had out degree at least one, then you could get a cycle, and that would contradict that it's a tree. So we find this sync, and then if you think about that sync, its bag is the one that definitely covers B, a contradiction. So why? Because, in each direction, so if it didn't cover B, right, there'd be a set somewhere, and then it should point kind of in that direction, right? But indeed, so it must cover the bramble. Okay, so we've proved the claim that there's a bag that is a cover of B, but since we have this tree decomposition of width less than K, it means that bags have size at most K, because again, the plus minus 1 thing. So then by this claim, every bramble has order at most K, the maximum size of a bag. So that proves the forward direction. Again, next time we'll pick up with the harder reverse direction. But in the remaining time, let's talk a little bit about large brambles. So which graphs have large brambles, right? We asked which graphs have large tree width, and we came up with this dual object, and we've claimed that there's this nice theorem proving this duality. That doesn't really answer the question, since we haven't yet answered which graphs have large brambles. So even though it is a nice characterization in the sense of NP co-NP type characterizations, right? Because to show low tree decomposition, I just have to show you the tree decomposition. Here's a tree, here's bags, you can check the properties. And then brambles are nice because I can, again, just show you the bramble as a certificate. I can say, here are the sets. You can check they're connected and mutually touching, and you can check that they have kind of low order. So that is nice, but which graphs have large brambles? So maybe pause and think for a moment if you can think of any. There's one kind of obvious one, is complete graphs have brambles of order K, right? And you kind of know they had tree with right, K minus 1, and so then they should have these brambles. And what is the bramble? Namely, you could just take each vertex, for example, and then this would be a bramble because they'd all be connected and mutually touching because of the edges. All right, but are there other graphs? What other graphs have large brambles? Is it really kind of just complete graphs, things like that, high density graphs? Turns out the answer is no. There's a really nice canonical set of graphs that have large brambles, and as we'll see in a bit, they're really the main reason a graph would have large brambles. So it doesn't have low tree width. So what are these graphs? These magical graphs are grids. So the K by K grid is the graph with vertices, all the pairs 1 up to K, and edge set I, J, I prime, J prime, where if you take the absolute value of I and I prime and J prime difference in sum, it's 1. Or otherwise, it's the grid as you know it. So where you take the box product of two paths. So you have this square grid. So this would be the 4x4 grid as drawn. So that's grids. And now the question is, do you see that actually grids have large brambles? So where is this bramble? So there could be multiple, but there's kind of a nice traditional canonical one, obvious one, and it's the crosses. So what are the crosses? The crosses of the grid are the k-squared sets Cij, where you take all of one row and one column. So you take row I and column j as your cross. So this would be the 2-3 cross, this blue part as depicted. So these are the crosses, and the claim is then this is actually, if you take all of them together, this family of sets is a bramble of order k. So maybe stop and prove that to yourself for a second. We'll discuss why afterwards. So if you've thought about it, why is this? Well, they're connected, check, so they meet that definition, and they mutually touch. They actually intersect, right? All the crosses always intersect in at least 2 points. So that's good. And then it turns out, how about the covering? Well, any row or column will cover the bramble, right? If I take an entire row, then every cross has to intersect the row, and same with the column. So that shows you could get a cover of size k, but actually any set of size smaller than k does not. So that's why, because it misses both a row and a column, right? If I only have k minus 1, then there's some row that's not in the cover, and there's some column that's not in the cover, and then hence there is a cross that's not in the cover. So that hence it fails to cover the bramble bee. So grids, canonically, with these crosses, have nice brambles. So there's something, even though they're nice, they're low degree, they're planar, etc., somehow this fundamentally is why we fail, why we'd have a large bramble. And actually, it's true in a very strong sense. So how do we know this? Well, there's the famous grid theorem of Robertson and Seymour from 1986 as part of their graph minors project. So just as they had introduced tree decompositions and tree width, they figured out that grids kind of are the canonical thing to not have low tree width. So they proved that there exists f of k such that every graph of tree width at least f of k contains a k by k grid as a minor. So remember that tree width is minor closed, and so if you had a grid as a minor, then you'd have to have, if you had a grid as a minor, you'd have to have tree width at least, k minus 1, but then actually they're saying that's the only reason, really. As long as you have f of k high enough, as long as you have tree width high enough, you actually have to have a grid as a minor. So really, up to the constants, up to the f of k, it really is the truth that grids are the main reason why you'd have large tree width. So we won't do the proof of the grid theorem here. So in older editions of D-Still, they had a version of it, so I think we'll skip it. But it's the original proof was kind of long, and there's now been successively shorter and shorter proofs. So there maybe are, 5 to 10 page proofs of this, but we're not going to do it. So it's a very heavy, involved theorem, at least more than, say, Brooks or Vissings or things that we've done in this class so far, but a very nice theorem. And I should mention, what about the f of k? Well, at first maybe they didn't really calculate it, or it was quite awful. I'll mention that Robertson, Seymour, and Thomas in 94 reduced it considerably to some kind of exponential in k, so like 2k to the 5th. And that's about where it stood. It was always exponential for the next 2 decades, and it was a very open question whether you could get a polynomial bound in f of k here. And in a very nice breakthrough, Shikuri and Chusoi in 2016 proved that there is some polynomial. So here k to the 98th was what they proved. And the best current bound is by Chusoi and Tan from 2019, which improved this to on the order of k to the 9th. And I'm hiding some polylog factors there, so it should be k to the 98th polylog k and k to the 9th polylog, but at least for the polynomial order, then 9 is the best at the moment. So very nice, and those are much more involved, these polynomial proofs, stretching maybe 20 or 30 pages, but to really optimize the number. Okay, so grids are fundamentally, the reason for large tree width, grid minors. And what else can we derive from this? Well, actually, there's a nice corollary of the grid theorem. So remember, we're talking about minors, and we wanted to understand a second question, which is, besides, quasi-ordering, was structure. What's the structure when you exclude a minor? So we did this for certain small complete graphs, but actually now we're prepared to do it for all planar graphs. So here's a nice corollary. Let H be a graph, then the graphs without H as a minor have bounded tree width if and only if H is planar. So this is a very nice corollary. So it tells you that, if you exclude a planar graph as a minor, you get bounded tree width, which seems like a very good structure theorem. It is a nice structural characterization. Well, on the other hand, it kind of tells you something that if you exclude non-planar graphs as a minor, you can't get such a nice characterization. So let's prove this. So why? So first let's do the direction that if H is non-planar, then we'll show they have unbounded tree width. So the class of H minor free graphs contains, so maybe pause and think about why this is obvious. Well, it contains all planar graphs, right? If you're non-planar, then of course you can't get then you can't get an H minor if you're a planar graph. And so then you actually contain all grids. So you contain all planar graphs, you contain all grids, all the k by k grids, and hence you'd have unbounded tree width in this class. So that one's kind of obvious. But what about the other direction? So suppose H is planar. The claim is then H is a minor of some grid, right? So why is this? So maybe pause and think to yourself, do you see why this is true? So every planar graph is a minor of some kind of some grid, some larger grid. So why I won't prove this to you, it is kind of obvious that if you embed H in the plane, so go ahead and draw down your H in the plane, and then superimpose like a super fine grid, so to whatever level of detail. And what you'll find then is that you can always then match up the vertices to the vertices of the grid, and then you can kind of snap the edges to lie along the grid. And you can do this, and that shows that actually you can embed H as a minor of the grid. Okay, so that's how you convince yourself H is a minor of some grid. And why is that good? Well, by the grid theorem, the class, if you exclude a grid as a minor, then you get bounded tree width. So thus, we get that the class of H minor free graphs has bounded tree width as well. And that concludes our corollary. So now we've learned something about the structure when you exclude planar graphs, and so this is quite nice, and it kind of gives a hint about the graph minor structure theorem I alluded to that characterizes it more for like all complete minors, is somehow planar graphs are special. So you might not realize this, but planar graphs are really special now in two ways, right? From this kind of corollary. One, they're the ones that exclude that when you exclude as a minor, you get bounded tree width. So they nicely answer that question, which seemingly has nothing to do with embedding, right? It's just a question, if you stated that, if you just define tree width, tree comp, that's just about trees. Minors aren't really about embedding. So somehow they're fundamentally the answer to a totally non-embedding question. And then number two, similarly, it shows you then that when you exclude non-planar graphs, you're going to get these planar graphs in the class, and so that maybe they're really the structure of planar graphs is that they are planar, that there's really no better description. And it's leading to the idea that when we want to understand excluding minors, that really you have to allow kind of planar graphs, and more generally graphs on surfaces, as somewhat of a basic class, that the best description of them in a way is that is via that class, that they're embeddings. So in some sense, it's saying that, if aliens only knew about graph theory, but even didn't know about geometry or topology or embedding, they would discover planarity based on these facts. They would realize that there's something special about this class. Okay, so where now do we go? Well, in the remaining part of this lecture, I just wanted to tell you about a fun game called Cops and Robbers. So it's related to the tree width duality theorem. So it'll prime us for maybe, even if we want to use this language for proving the harder direction, but also it's a really nice way to think about what does the tree width duality theorem really mean, and how to maybe internalize it. So what's the game? Well, at GB a graph, then here's how we're going to play, there's going to be kind of two players. There's going to be cops, so k cops, each of whom at any time are either they're standing on a vertex of G, so they're kind of patrolling that vertex, or they're up in a helicopter, so they get to move around, so they can take off from the vertex, be in a helicopter, they're removed from the game, and then they can go around and land on some other vertex and keep doing this. So those are the cops. And then we'll have a robber. And what does the robber get to do? Well, they're going to be infinitely fast. So think, arbitrarily fast, and they can run at any time. So if they see a cop coming in this helicopter to land on their vertex, they can run. They can run away. They can run to anywhere they can get to. Well, that wouldn't be much of a game if they could just run anywhere. We're going to prohibit that they cannot run through a cop. So that's the main thing, is they can run, they see it coming, but somehow if they're surrounded completely by other cops, then they're trapped and they'll get caught. And importantly, it turns out we're going to require that the robber is always visible to the cops. So you can't really hide. They can always see where you are. You're just relying on the fact that you can run really fast to try to elude them. So as suggested, how do you win, or who wins? Well, the cops will win if they land a helicopter on the vertex occupied by the robber. So they're trying to catch the robber. So if they can land a helicopter on the vertex, then they'll win. Now again, that would kind of mean that the robber couldn't go anywhere. That there have to be the cops surrounding all the adjacent kind of vertices. And then the robber wins if it eludes capture. So as long as it can always elude capture, no matter what strategy the cops employ, if it can always stay safe and stay uncaught, then the robber is said to win. So you can debate whether you think of this as kind of a finite or infinite game. It's clear, though, that actually the cops could win in a finite number of steps because it's a finite graph. So you could phrase it as that, but maybe it's better to think of it as infinite. So these are the cops and robbers. So this might seem silly. It maybe makes sense to you, though, as a kind of a graph searching kind of game, graph searching parameters that you're trying to search through a network, through a graph, a database, and you're trying to pin it down, kind of thing, and trying to it has applications beyond just cops and robbers. But why is it useful? How do you think of it? Well, what is the winning robber strategy? So a winning robber strategy is essentially equivalent to the following. If you think through that kind of definition, we're going to call it a haven. So let G be a graph. A haven in G of order k plus 1 is a function beta which assigns to each subset x of V of G of size at most k a component of G minus x such that beta of x touches beta of y for all x and y that are small subsets. So how should you think of it? Well, basically, wherever the cops position themselves, the robber kind of can pick a home base, right? So they need to pick a vertex to be standing on, but really at that point, it's equivalent to stand on any component of G minus x. So if you think that x is the position of the cops, they need to pick a component as part of their strategy. Some vertex, but really equivalently kind of a component to be in. And then they need the ability, though, then to be always touching. That they can always get from where they are when they're in position X to where they want to be when they're when the cops are in position Y. So we won't go through that, but essentially that's what it's equivalent to. And here's a nice proposition: is that how does it cops and robbers relate back to Brambles and tree width? Well, a graph G has a Bramble of order k if and only if it has a haven of order k. So in the definition there, I wrote k plus 1 to align with the k cops, but let me just prove this instead of k plus 1 and k plus 1 with k and k. So if you have a graph G as a Bramble of order k, if and only if it has a haven of order k. So proof, so let's go through this, or if you want to pause, you could think through it yourself, but if you have a Bramble of order k, let's do the first direction, then for each x that's small, how should we pick our haven? Well, it's kind of that same trick, right? Since the x won't cover the Bramble, because it has order k, there has to be some set in the Bramble that's disjoint from x. And if you then think about it, you'd pick the beta of x to be the kind of the component of G minus x containing h, right? So actually, similarly, like kind of all the sets would actually live in a direction, and so this will be well defined. So we'll let beta x be that component, and then beta is a haven of order k. You can just prove that they're actually always touching, right? Because the underlying the set that they contained will be touching, and so more generally they will be touching. Okay, so that's Brambles into havens. So you just kind of pick the component that contains the Bramble to make the haven. What do you do if you have a haven? Well, you just there is your Bramble. It is these components. It is these sets. It is these beta of x. That itself will be a Bramble, because then they'll all be touching. And of course, they can't be covered by a set of less than k, because there always has to be some beta x disjoint from any x less than k. Okay, so that's showing you this. So somehow, if you thought of Brambles have this nice touching property, this pairwise touching connected set property, and kind of havens are kind of generalizing that a bit more. So they're kind of a larger structure, but essentially equivalent. Okay, so that's the robber strategy. What about a cop strategy? What is a winning cop strategy? Well, I'd like to claim it's essentially a search tree, where what do? You kind of think, if you mapped out a strategy for the cops, it would mean that for each vertex of the tree, they'd have a position for the cops. They'd be where they are, and we'd have, say, the robber in some component of G minus V of T. And then the tree would branch depending on how the robber moves in the response to the cop. So kind of the cop would make their move, they're up into helicopters, and then the robber gets to run to some new vertex, or really more generally the components from the cop's position. And then depending on where the robber ends up deciding as its move, its home base, then the cops will alter their strategy. They'll branch the search tree, saying, okay, well then we'll keep moving this way. We'll move here, or then we'll move here if they're in this component, and so on. And eventually they need to catch the robber. So that's a search tree. Now that might sound familiar to an object, but let's add it additionally. So there's kind of that really is just any strategy. It could be any such tree. And we'll say there's a particularly nice kinds of strategy which are called, we'll call monotonic. So winning cop strategy is monotonic if whenever a cop leaves a vertex, then no cop ever returns to that vertex. So that's what we'll use there. But then no cop will ever return to that vertex. So it's kind of saying that indeed we're monotonic if we're monotone in how we use the cops. So we don't want to be kind of wasteful and send a cop to police a vertex and then have them leave and have to come back. It's in some ways, if the robber wanted to be at that vertex, you should have caught them then, right? It's saying, as we're kind of sweeping, we're doing this in a monotone way. That we never have to have a cop double back and go back to one that was already policed. So that's a winning cop strategy, monotonic, and do you see what this is equivalent to? So maybe stop and think about what would it mean for the search tree, and then more generally, what such strategies are equivalent to. Okay, so let's move on. Namely, for that first part it's saying that if you think about all the nodes where there's a cop at that vertex, then call that TV, that would have to be connected, and hence it'd have to be a subtree. So really, monotonicity is imposing kind of a connected or subtree condition on cops being at a vertex. And so if you pair that with the following observations, that in order for the cops to win, recall what you need. You need to catch the robber. So what does that mean? It means that every vertex needs to be occupied by a cop at some time, right? Because if there was a vertex which was never occupied, the robber could just sit there the whole time. So obviously every vertex needs to be occupied by a cop, but if you think a little bit more, actually every edge needs to have both cops on its ends at some time. So there will have to be a point where every edge also gets covered like that. Otherwise, then there could have been a time where kind of, the robber would just stay between the two ends of the edge. And, if a cop lands on one, okay, I'll run over to the other side. And since you never occupy both at the same time, I can just ping back and forth between them. So when you put those two together, so every vertex needs to be occupied says that the TV are indeed a non-empty subtree, and the other one says that every edge indeed appears kind of in the bag from the cops. And what is that? That's really then just clear. The following proposition holds that a monotonic winning cop strategy is equivalent to a tree decomposition of width strictly less than k. So again, subtracting the 1 because that's how we defined widths. So basically the size of the bags would be the number of cops, the maximum size of a bag. So that's monotonic winning cop strategies are clearly tree decompositions. So somehow if we had defined tree decomposition without the connected bit assumption for these TVs, then that would be kind of general strategies, and the monotonic is let's also kind of make them kind of connected. And then now we can really put into context what the tree width duality theorem says. So here's an equivalent formulation, is that k cops have a monotonic winning strategy if and only if they have a winning strategy. So obviously if they have a monotonic winning strategy, they'll have a winning one, but really it's saying that these are equivalent. So if you could win, right? Because what's the point is if the robber can win, that's having a bramble. We've established that robber strategies are related to brambles and havens more generally. And so if you assume they don't have that, then the tree with duality theorem says you have to have a nice tree decomposition. And that would mean be equivalent to being monotonic. So that's really another way to think about it. Obviously, either the cops or robber win, but it's not clear that the cops should be able to win monotonically. Also, maybe it wasn't clear that the robbers should we should be able to refine their strategies from this more abstract notion of havens down to brambles, which are really more of a tangible object that you can point to and verify. But we are able to do that too. So next time we'll look at proving this. So it seems kind of obvious, shouldn't this be obvious? But really it's not at all. So it's going to take us, it takes maybe a couple pages to prove. So it'll really take us a full lecture to prove this tree with duality theorem. And the way we're going to do it, we're going to even need the use of Menger's theorem. So we're going to need some ideas there to get this done. But now we've kind of bookended, we introduced tree width and tree decompositions, and now we looked at brambles, and grids are the ones that contain large brambles, and there's this very nice grid theorem that establishes that indeed, it's having a large grid minor is the equivalence to having large brambles to large tree width. So we talked through that and what it meant for planar structure theory, that it's only planar graphs that exclude to get bound to tree width. And now we went through cops and robbers, the game, and talked about how their strategies are related, and it's kind of just another mental way to think of this tree with duality. And so next time we'll prove indeed that these monotonic winning strategies, if and only if they have a winning one, we won't do it in the context of the game, we'll do it in context of brambles and tree width, but we have that to look forward to. So until next time, see you then!